Hey there, in this video we're talking about copy constructors and static members and friends and generally more things you can do with classes in C++ programming. And this covers sections 14.1 to 14.4 in the Gaddis textbook. Now a little side note, at this point the course is going to start accelerating a bit. Starting with this video, we're mostly going to focus on an overview of the highlights, the really important parts of each chapter, particularly the things that we need in our course. And as usual, if you want to see all the details and extra examples and things like that, definitely read the book for all the other stuff that we don't have time for here. Okay, copy constructors. What's that about? So we talked about copy constructors before in chapter 13, and we know that constructors are for initializing or setting up an object in a particular way. You can overload the constructors. We already know you can have 1 or 2 or 3 or 4 constructors depending on what's useful for your application programmers to initialize their objects to begin with. And so here's another one. Copy constructors are a special kind of constructor that are used when a newly created object is initialized to the data of another object of the same class. Now, why do you want to do this? First of all, think about this. Something as simple as an initialization, an assignment, like A equals B. Okay, that's making a copy. Anytime you write down A equals B, you're making a copy of the contents of the B variable and putting it in the A variable. Of course, that's making a copy. And we've needed that in lots and lots of algorithms that we've done. Take one variable, make a copy of another. We've used that in our swapping code, our sorting code, find the minimum algorithm, find the maximum algorithm all the time. So generally speaking, our objects are going to need that kind of capacity for almost any program that they work in. Maybe a more concrete example. You're working on a fantasy role-playing game. You're spawning monsters in the world for your players to combat and fight against and get treasure from and so forth. So probably the way that you're going to spawn those monsters is you're going to have prior pre-existing monsters and you make a copy of one. You make a copy of the monster object that already exists, and then maybe you modify a couple things. Maybe you modify the hit points to distinguish them perhaps, but it's mostly the same as the other types of monsters. So if I'm making a fantasy role-playing game like that, I would want a monster class with a copy constructor so that I could easily spawn new monsters when I wanted to based on prior ones. Okay, so of course you want to do this. So let's see how to do that. Now to begin with, C++ already provides a default copy constructor for you that does a very simple job. It just copies all the member fields of object A into object B. Already does that. Very simple. Just use the equal sign. We'll see that on the next slide. And that default copy constructor works fine in many cases. So a lot of the time, you, the class programmer, don't have to do anything to make that happen. There's already a copy constructor that kind of does the obvious job for you. But we're going to see a little detail that it actually doesn't work all the time. And therefore, you might want to take control of this and intentionally write your own copy constructor. All right, so here is how you trigger the copy constructor. You just use that equal sign assignment. That actually does a copy job. So you can use the equal sign to assign one object to another, or at the moment of initialization, to initialize an object with another object's data. So if I have some kind of fancy class and I've made 2 objects, instance 1 and instance 2, I can just do this. I can just write down instance 2 equals instance 1. And I mean, you already know that works for ints or floats, but it works for any kind of object as well. So a student object, a contact info object, an inventory item object, whatever it is, just put down this equal for assignment, and you do copy all the member values from the thing on the right, which in this case is instance 1, right? So everything on the right, all the member fields get copied into the corresponding member fields of the thing on the left, which in this case is instance 2. So if I have a name and if I have a name and an age and an ID and a description and a GPA, all those things get immediately copied into the corresponding members of the object on the left. Okay, you can use this at initialization. So if I'm declaring a rectangle called R2 and I already have one called R1 that's set up for me, I can just put down equals R1, and as the R2 object gets created, it copies all the members into R2. Okay, so hopefully that's pretty clear and pretty obvious. And that is automatically built in to any class that you create in C++. That's the default kind of obvious thing to happen, and that does actually get built in without any extra work at all. Nice. But it's not what you want all the time. Here's why. Okay, the problem is, what if one or more of the members of your object are actually pointers holding the address of dynamically allocated memory that the object is responsible for controlling? And we've certainly seen examples of that in the past, like the contact info class from chapter 13, that as you make this object, the constructor dynamically allocates some memory. Okay, you got a pointer holding where the data is while the object is alive. And then, of course, when the object goes out of scope, the destructor of that same object has the responsibility of cleaning it up. Okay, so we've seen that before of an object that's got pointers to memory, and it does have the responsibility of taking ownership of what's in there. So let's make a reduced example of that on this slide. So here we have a class called SomeClass. And looking down at the private data here, just has one piece of private data to make this very simple. It's an integer pointer called value. And of course, we're going to be using that integer pointer to dynamically allocate an integer and keep track of where it is on the heap. Of course, in practice, it would be something larger than that. It'd be like a large array or some more complicated structure or something like that. But we're just kind of boiling this down to the very essence of what the issue is. So just one integer pointer where there's an integer that's dynamically allocated. Here in the public functions, you have a constructor SomeClass, takes in one integer number called val. Now, by default, it's 0. So if the application programmer doesn't put anything in there, it's going to be 0. That's a little side point there. But here's what the constructor does. Okay, dynamically allocates a new integer, takes that address, stores it in your value pointer, and then once you've got that, dereference value and store this incoming val in it. Again, very similar to that contact info example from chapter 13. So you got to declare the integer, right? Once you have that, then you can actually store this number val in it, of course. And then you have standard accessor, standard mutator. We don't see the code for that. Of course, you know what that's going to look like. So you call getVal, and it returns that integer that's being stored in this object. And if you want to change it, of course, we have a mutator here called setVal. And you send a new integer, and of course it would dereference value and save the new integer there. Okay, so a very small little class that basically controls a dynamically allocated integer, and you can get it and you can set it, of course. Okay, so what you're going to see is that the problem is that if you use the default copy constructor on this, if you make a second object like this, and you do the standard default copy job, okay, it's going to copy value, which is not the number, but the address of where it is. So what you'd be doing is you'd be copying the address into object 2's pointer, but then this val that you stored, that's a totally separate issue. You're not copying that. Okay, let's see the detail on this. So the problem here is that if you do a memberwise copy for objects that are controlling dynamic memory, you're copying the pointer, but now you've got two pointers aimed at the same data location, and you have two objects that are in conflict over what's really one single piece of data. And so some people call this a shallow copy. Let's see how this works in this little illustrated example here. So first of all, this SomeClass example, I make object 1 and I initialize it to 5. Okay, that's the kind of this box over here on the left. So I've got object 1. I have value, which is a pointer holding some kind of address. We're not showing this here. Of course, it would be in hexadecimal. An address pointing to where this number 5 is. Okay, and probably the idea is that this object 1, again, is controlling that data location because it created it. Now, the next thing that happens here is that I'm declaring another SomeClass object called object 2, initializing it with the equal sign to object 1. The default copy job happens. So I've made object 2. It has its own value pointer, but it only copies in the pointer address. So whatever the address of value is in object 1, I have the exact same address in object 2. And of course, both of these things are pointing at the data location where there's the 5. So in some sense, they have co-ownership of it, right? They both have access to the same single piece of data. Now, the third line here is, let's say I call object2.setVal and send in a 13. All right, that totally works. So the setVal mutator happens, and you go and dereference value, and you assign the number 13 in here, and notice that the 5 is gone. The 5 has gotten overwritten there in that one location. And so now, if for some reason the program needed to refer back to object 1, let's go back to object 1.getVal and print that out. Now it says that's 13. Okay, now, maybe in some cases this is what you want. Maybe you actually wanted just one single data location with 2 objects that both refer back to it. Like I could imagine that in a case of immutable data. Like we talked about, the contact info example actually has immutable data. There's actually no way to change it. So if that was the case, if you didn't have any mutators and there was no way to change that data, then actually this would be perfectly fine. Why not have 2 pointers aiming at the same data, because you can't change it and you're saving some memory, frankly. But for an object that has mutators that looks like it ought to be owning its own integer, this seems very bad, because I told object 2 to store the number 13, and now object 1 looks like it also has the number 13, and the 5 that it was trying to own is just gone. So in a lot of cases, if you have a mutator, that seems like a really bad problem, that object 2 is actually overwriting and deleting all the data from all the other objects of the same class. That seems bad. So if that's not what you want, let's see how you would fix that. So this is the case where you'll have to make your own copy constructor to take control of this particular process. It's not too hard. So here's a programmer-defined copy constructor, and this is what allows us to solve that problem with objects containing pointers to dynamically allocated memory that they are responsible for controlling. So here's our copy constructor here. Of course, it's going to be in, for this example here, we're calling the class A class. Don't forget that constructors must be named the same as the class. So here's the name of this function here, my constructor A class. And every copy constructor always has one parameter, and it takes a constant version of the same class as a reference. Okay, so I have an A class coming in as a reference, and we've also got it tagged as const, and we happen to be calling it obj for the object here. That's the object that you're copying from. Okay, and you're going to take all the data from that and copy it into the object that we're creating right now with this constructor. So continuing with that same kind of example here, so now if you want this object to actually have its own dynamically allocated data location, here is where you dynamically allocate the new integer or array or structure, whatever it is. Here we're declaring a new piece of data on the heap, storing that pointer, storing that address in our pointer value, and secondly, copying the data from the original object. So whatever you passed in for obj there, go to obj.value, which itself is a pointer, right? Dereference that, so now you actually have the value in there, and then you can save that in the dereferenced value address here. So at least to begin with, this new object will be holding the same number as the old object, but it's in a second location. So this new object does have its own data location that it can control separately from the first one. Now notice again, you might want to take a piece of paper and write this down, right? As you see this new syntax, this new notation here, for the first time that you have to use it at some point. The copy constructor, again, takes one parameter. It takes a reference parameter to an object of the same class. Okay, let's just think about that for a second. So obviously you're making a copy of an object of the same class. That makes sense. Why is it reference? Well, it's probably really big. Our classes have quite a bit of data in them. So we want to make it a reference so you don't have to arbitrarily copy all the information again on the CPU just to get it into this function. That would be wasteful. So we'll probably be passing big things around as reference. Okay, but on the other hand, that would allow the function to change that stuff. And in a normal copy or assignment job, you shouldn't be changing the thing that you're copying from. So we've also tagged it with const to make absolutely sure you're not changing the thing that you're copying from. And so that's why that normally looks like this, constant reference to the same kind of object. All right, so let's kind of map out how this one works differently from the prior example. So now that we've got our programmer-defined copy constructor, each object now points to a separate piece of dynamic memory. And some people refer to this as a deep copy. You haven't just copied the pointer, you've also copied the structure that the pointer points to. So in this case, I make a first object of some class. Here's object 1. Again, creates it, dynamically allocates some data, puts the address in the value pointer, right? Puts a 5 in the data location. Great. And now here we're making a second some class object called object 2, set it equal to object 1. Now again, this equal sign is what triggers the copy constructor function on the prior slide. So just put down equals for assignment, and you jump into that copy constructor and does that job. Dynamically allocates a piece of memory, stores the address and value, copies what's in this first location over. So at least as we get started here, now I have this object 2 with its own value holding a different address, pointing at a different data location, which also holds the 5 that we've done a deep copy on. Now, let's say you call object 2's mutator setVal13, and let's see what happens here. Well, of course. So in this case, you're only changing the data location pointed to by value, and that's the one that object 2 has full and complete ownership over. It's not in conflict. It's not arm wrestling some other object for it. That's its own thing. And object 1 here still has its original data location, still has the 5. Then the prior example got wiped out, which we didn't like. And now if you want to check on that, you call object1.getVal, and you will see it is actually storing the 5 still. So here, each object legitimately has its own data location to track its own data. And what looked like a problem for us before is now solved. But we did have to add the programmer-defined copy constructor and actually specify the dynamic memory allocation, because that part C++ will not automatically do for you. Again, sometimes you want multiple objects pointing at one thing, because that could save memory, again, for immutable objects. Sometimes you want each object to have its own dynamically allocated memory that it owns. And the C++ compiler cannot make that decision on its own. You, the programmer, have to decide which situation you're in and take control of that with the copy constructor. Okay, second thing for this video, let's talk about static members, starting with static member variables. So hopefully you've seen that keyword static in C++ before in first semester programming. We very, very briefly mentioned it. We didn't use it a lot, but we very briefly mentioned that if you make a local variable static, that means that it's sitting in one place in memory. It's fixed in memory, and it doesn't get created and then get deleted and created and get deleted every time you call the function. There's just one version of it sitting in one place in memory. Okay, so this is a little bit different, but hopefully the word static brings to mind what's going to be happening here. A static member variable in a class is a variable with only one fixed copy in memory for the whole class. Now, this is different from all the other member variables that we've seen so far in chapter 13 or 14, and technically all those other variables we would call instance variables. There's a separate copy owned by each object. Just like that prior slide, right? Object 1 has its own value pointer, and object 2 has its own value pointer, right? Separate copies, separate versions of that member variable for each object that each object owns. Now, if you make a member variable static for a class, that goes away. Now, there's just one single version of that variable for all the objects in the whole class. Objects do not own separate versions of that variable. There's literally just one for the entire class. So one thing that we commonly do, why would you want to do that? Static variables are often used for making class constants. If you have a constant inside a class that a lot of your members have to use, we frequently make the constant static so that you're not wasting memory with every single object having a separate copy of that one fixed number. Why bother? So if I have like a trigonometry class or something like that, and I need a constant for pi, I would probably make static const float pi equals 3.14, et cetera, et cetera. And instead of making lots and lots of objects and wasting lots of memory, make that constant static, because you only need one of them. That makes sense to me. Other slightly more exotic uses would be tracking resources used by all the objects in a class. And the book has a fairly interesting example. I think it's got a tree class that automatically keeps count of how many objects were made of that class, which is kind of interesting. And again, once the class programmer sets it up, the application programmers don't have to worry about that. It just keeps count of how many objects are out in the world automatically, which is kind of neat. So you might want to look at that tree example in the book. If it's not obvious already, you declare a member to be static by using the keyword static right in front of the declaration in your class. So again, like static float pi equals what pi is equal to. All right, so static variables, commonly constants in a class. There's only going to be one version of that variable. Now, in addition to static member variables, you can also make static member functions. Let's look at that. So a static member function is a member function, kind of same theme here, which does not vary for different objects in a class. So at least conceptually, we usually think of the member functions in a class, each object having their own version of that. So if I have a rectangle class and I have a member called setLength, I'm thinking that every single rectangle has its own setLength function. Now that's a little bit of an illusion, but I am thinking that if I call setLength for object 1, it's changing the length variable in that rectangle. But if I call setLength for rectangle 2, it's changing the length variable in that rectangle. And of course, those are different pieces of data. So conceptually, it seems like those functions are doing separate jobs. Now, similarly, if you make a function static, that's not the case anymore. Objects don't have distinguished functions. There's just one. Again, static means just one fixed version. Just one fixed version of that function for the whole class. So sometimes we do that. If there's a function that doesn't need to access any member data, why not do this? There's some kind of advantages to this. So if you do make a static, if you make a function static, now you cannot access instance variables. You can access static member variables because there's only one for the class, and there's no mystery, there's no ambiguity to which version of that variable you want. But since you can't access the instance variables, or I should say it doesn't make sense to access the instance variables because a static function, if there's only one version of this function, I get in there, hypothetically, if I try to access a member variable, as the compiler, I would say, well, which one do you want? Do you want the member variable for rectangle 1 or rectangle 2 or rectangle 3? Which one is it? Because there's only one version of this function if it's static, and now I don't know which object you're talking about. So that just doesn't make sense, and that's impossible. So static functions, things that don't need to rely on the member data because you have the perspective of being in the class instead of one of the objects. Now, one of the advantages here, one of the interesting things is once you do that, and once you accept that this function cannot access member data because it's not actually in an individual object, now you can actually call this kind of function on the class itself without creating any objects first. For example, if I have a class called die, and this is one of the major examples back in chapter 13 that you might have seen before, if I have a class called die, I can make, several dice. I could make die 1, die 2, die 3, die 4, of course. But if I have an initialize function and it's static, then I don't need to call die 1 initialize or die 2 initialize. I could just call die class, scope resolution operator, and call initialize. And maybe that initialize function sets up some important stuff for the whole class, like maybe it initializes the random number generator. And you only need to do that once for the whole operation. You don't need to do that separately for each die object. Just do it once. So that's a really good example of a function that I would want to make static and just call that function one single time on the class as my program boots up. Right? Conceptually, it's not something that I would have to do for each separate die object. And there's a couple more examples in the book, so I encourage you to look at that. Static member functions. Yeah. Okay, so what else are we talking about? Now this is interesting. So the this pointer. So this is a little piece of hidden mystery that is actually in all the classes you've made so far, but it's handled automatically by the compiler most of the time. And so this is another one of these things that's automatically happening in object-oriented programming that's saving you a lot of time. So there's a keyword, this, in C++. If you type this, it's going to show up in boldface in Dev C++ because it's one of these special keywords. It's a predefined pointer that's available to a class's member functions that points to the object that you're in. It always points to the instance, the object of the class whose function you're currently calling. So it actually is it's pointing to the object that you're currently in. And interestingly, it's automatically passed as a hidden argument to all the non-static member functions. So this is one of these things whereby if you were trying to do this kind of job in the C language that doesn't have object-oriented programming, you would have to pass the pointer to the data that you're talking about into every single function that needed to access the data. But in C++ with object-oriented programming, that just automatically happens with no extra effort. So you didn't know about that before, but actually every single instance function has an extra argument being passed into it, which is the pointer of where the object is in memory. And if you want to, you can access that with this. And a whole bunch of reasons you might want to use that. You might want to use that as a return value from a function. You can pass it to other functions that need a pointer to an object of your class type. Might pass it to other functions as a parameter. A whole bunch of uses for this, as a matter of fact. Okay, let's think of just like one very simple example that I can think of that I use this for in my own code. So one thing I think of that honestly has irritated me a little bit in the last couple of lectures is that all of our class functions, like our mutators and our constructors, have been mangling the parameter names going into the functions so as to distinguish it from the member names. So if you go back to the rectangle class and there's this member set width, you're passing in a number to be the new width for the rectangle, and we named that argument here, this double, we called it W. Okay, now what you're going to do with that, of course, is take the W and just set it into the width member of the rectangle. But at least in my first semester course, I was always emphasizing, don't name variables one letter. I was saying that over and over again. We never do that. We don't name variables one letter. We want it to be more readable and more clear for other programmers exactly what this is. So what I would prefer to do is I would like to make this argument width, but I can't because that would be in collision with the member variable width. So that's why we've been doing this all along. So we called width W and we called length len, stuff like that. And I really haven't been happy with that because it's not really clear and readable enough. So we can solve that problem, and this is what I do in my code quite a bit, is if we use the this pointer, we can more easily distinguish the member variable from the parameter variable. So now, personally, I would probably do this. Here's my rectangle set width function, and here, the incoming argument, this double, I actually am calling width. Great, very, very clear, very, very readable. And then what my one single statement here is I take that width and I assign it into this pointer width, right, which is different. So this, again, that's a pointer to the rectangle object that I'm inside of, and then I'm using this arrow notation. Follow that pointer address, go to the actual rectangle data, go to the width member, and then take this number and store it in that. So width, this width here on the right, is referring to the incoming argument, and this arrow width is referring to that member variable in this object, this current object that I'm dealing with. So I do this quite a bit actually in my member functions so that I can have very clear readable names as normal for the incoming arguments, but I can distinguish between the arguments and the actual member variables by using this. Now that's not the most overwhelmingly important example, but that's just kind of an initial example of this is something that does exist inside a class function, and it does refer to the object that you're currently inside of. Now, I could go back up here, and this actually explains a couple of things about, this explains how the member functions actually access the correct member variables. Let me go up to this original example again. And I could ask, and this is a trick question, honestly, I could ask, how many arguments are coming into this function? How many arguments does this function have? Okay, And again, the trick question, the answer is 2. There's this W coming in, but there's also this, right? This gets passed in as an automatic, invisible, hidden argument. There's actually 2 arguments coming in. You get the this for free. That happens all the time. You don't have to do any work for it. And over here, when we actually run this statement and we pass something into with, how the C++ compiler actually interprets it is like this down here. So that's how it figures out, if I have 1, 2, 3, 4 rectangles, which version of the with member to pass data into is it's actually using the this pointer to go to the right data location. So you see this, but what the compiler does is actually this second version down here. So for me, I don't mind making that explicit as a matter of fact, but that actually explains how C++ manages to go to the right data location every time you call a particular member function. It is actually using the hidden invisible this pointer. And again, if you want to use it, it is available for you. Great. It also, so this is one of these things that's saving you some typing time as a C++ programmer. Every single member function has this extra argument that comes in for free. And you don't have to do any typing for that. That's kind of nice. And it also explains why static functions work differently. Because if you mark a function called static, like we were talking about in the prior slide, then it doesn't bother to send in a this pointer. And then you don't have one specific object that you actually are accessing. Again, you have to talk about the whole class in general. For static functions, you can refer to static variables because there's only one of them. There's no ambiguity about that. But without the incoming this pointer, there's no particular objects, instance member data to access. So that actually does explain exactly how the static functions work if you think about it. All right, so kind of a simple example on this slide here. In the next lecture, we'll see at least 1 or 2 more examples that might maybe be more interesting, so be on the lookout for that. Okay, last thing in this lecture here, friends of classes. So again, friend is a keyword in C++, and a friend is a function or a class that is not a member of a class, but still has access to the private members, right? That ought to feel very strange to you, because the whole point of marking members as private in a class is that nothing outside the class can access them. So marking something as a friend shortcuts that and is a way to permit other code to access private members, which normally shouldn't be happening, frankly. So a friend function can be a standalone function, like a semester 1 C++ function, or it could be a member function of another class. And if you're doing that, then you declare a friend of a class with this friend keyword in the function prototype. Now, I don't think I've ever used a friend function ever in my C++ programming. I kind of don't like the idea because to me it feels like it's breaking the whole security principle about marking things private in the first place. Mark things private so that other people cannot access them. So I kind of feel nauseous a little bit about marking something as a friend because you're breaking the whole security feature about what private's supposed to do, breaking that data hiding. So it's generally kind of frowned upon. You don't want to do that unless there's a really overwhelming reason for that. I guess the book does have one single example of something that really would be useful to do that. I don't think I've ever used this. I would recommend staying away from it, honestly. But it does exist in C++, so you should know about it. Enough about that. So I think that's a pretty good highlight of the first half of chapter 14, more about classes. And what I do with my students here is I would have a lab with them where we would look at this example in chapter 14 called the feet inches class. And boy, what a great example this is. I'm going to keep coming back to this again and again in the next couple of lectures because I think it's a really great little example of a class that holds some kind of data and we want it to do like fairly natural things in our next several examples of programs. And of course, what this is representing is it's representing a measurement that you would do in the imperial system where you are measuring a distance in feet and inches. So you might be doing this, again, maybe in the United States here, if you're a carpenter or you're a stage designer or you're a painter or something like that, you're measuring some kind of distance and you're recording that in feet and inches. 3 feet 6 inches, 12 feet and 8 inches, something like that. And so obviously there's it has two components to it, two member variables. It's got the number of feet and it's got the number of inches, of course. And don't forget that there are 12 inches of the foot. So if I measure up to 12 inches, that really ought to be one more foot, right? And among the things that we're going to be seeing in this lecture and the next one is I would like to be able to add two of those objects. I would like to be able to subtract two of those objects. So to begin with, and we'll continue to talk about that. So you ought to get familiar with this feet inches example. It's a really great example. And so in the next lab with my students, I would look at this feet inches version 1 as we start to kind of build out and expand on it, read the specification and write a test driver to test the public functions that are in version 1. Of course, there's a constructor, there's a setter, there's an accessor, things like that. And what we would also do is we would think about this lecture here, add a copy constructor. So add a copy constructor to make sure that I can initialize one of these feet inches objects to another one, because we might need to do that a couple times. So that's kind of a good example there of take some existing code in the book and then add a little bit to it, namely a copy constructor, and make sure that we understand that. So yeah, so think about that. If you have access to the book's lecture code, take a close look at this feet inches class, and we'll be relying on and referring back to that quite a bit in the near future. So next time, in the next video, we're going to be looking at the back half of chapter 14 for a very interesting topic called operator overloading. Of all of the symbolic operators, or most of the symbolic operators in C++, like the plus sign or the minus sign or the times or the divide or the equals or really anything, you as a C++ programmer can take control of that and make them do whatever you want. And what an interesting, powerful feature that is in C++. For example, like one of the things that we'll be doing then is to take two of these feet inches objects and use the plus sign to just add those objects. And it's going to automatically add both the feet and the inches and then also normalize it if the inches go over 12, just by putting down plus. It's going to do all that work for us automatically. And honestly, we've been relying on operator overloading for some of the things that the string class does for us. Like a plus sign there concatenates the two strings, glues them together, right? So a really interesting, powerful technique in C++ that doesn't exist in a lot of programming languages, as a matter of fact. Operator overloading, taking control of the symbolic operators to do whatever you want. So hopefully, when I first saw that, boy, I was so excited about it. So I really hope you'll join me for that, and I'll see you then.